Hello everyone, my name is Igor Califrer, and in this video I'm going to introduce and briefly outline the results from our recently published paper called Proximity-induced zero energy states indistinguishable from topological edge states. So as many of you know, one of the interesting features in topological insulators is the presence of these edge states. There are states that have zero energy and are highly localized at the boundaries of the topological insulator, decaying exponentially into the bulk. We call the finite region in the phase diagram where these states are present the topologically non-trivial phase. In this work, we have noticed that when a topological insulator is put in a junction with a normal metal and the energy levels of the normal metal are tuned to zero energy, some states might appear that mimic the characteristics of the topological edge states. We have tested this effect in 3 different junctions between topological insulators and normal metals using 3 different prototypical topological insulator models, namely the SSH model, the Kitaev superconducting chain, and the 2D Chen insulator. So first, for the SSH and M junction, as I mentioned, we varied the chemical potential of the normal metal, and as you can see in this plot over here, the energy levels of the states in the junction change with the chemical potential of the normal metal. So I have marked here 4 states, marked as circles with different colors. The blue circle is the topological edge state. You see that it is localized at the interface between the SSH and the normal metal. And you also see that it is localized only on the even sites. As we move away from zero energy by increasing the chemical potential of the metal, you look at this, the green circle, which has an energy that is different from zero, and its characteristics deviate already from those of the topological edge state. It is no longer localized on the even sites, for instance. As we move further away from zero energy, you look at the purple circle and the edge state is completely lost. But as the chemical potential of the normal metal is tuned, eventually states from the normal metal part cross zero energy. And this you can see from the orange circle. We have observed that this state has characteristics that are similar to the true edge state. And this orange state we are henceforth calling the fine-tuned state. And this state, as I mentioned, has, you can see that it is localized at the interface between the SSH and the normal metal, and also it is localized at the even sites. This that I have presented is in the topologically non-trivial case, where initially we already had a topological edge state that I've shown was the blue circle. Now, what is interesting is that even in the topologically trivial case, when we tune the energy of the energy levels of the normal metal, and when these states cross zero energy, we have observed that a state arises which has the characteristics of the topological edge state, even in the topologically trivial phase. So here is a plot of the energy versus the chemical potential of the metal. I've marked here the point where this state crosses zero energy. And at this point, this plot is a plot of the spatial profile of the wave function of this state. And you see that it is localized on the odd sites this time, but that it decays into the bulk starting from the interface between the SSH and the normal metal. Moving on, we have tested this effect in the Kitaev and M junction. In this model, the so-called Majorana modes appear, and these states is such that they are their own antiparticle. So in the tight binding model that we use, where we have electron and hole components for the states resulting from this Hamiltonian, the electron and hole components have the same absolute values. So here is a plot of energy versus chemical potential of the junction, of the normal metal in the junction. And the state at zero energy is the Majorana mode. Here is the plot of the two components of these Majorana modes, marked as psi-e and psi-h for spatial profile of the electron and spatial profile of the hole component. And you see that they have the same absolute value. In one side, they are shifted by a minus sign, and on the other side, they are the same. And this property of the Majorana mode also leaks into even into the normal metal part. So in the topologically trivial part for the Kitaev NM junction, we have fine-tuned the chemical potential of the metal, and you see here on the upper left how the energies vary as a function of the chemical potential of the normal metal. And as we approach zero energy, here I have marked one of the points where this happens, and you have a pair of states that approach zero energy. So I marked the two states before crossing and after the crossing. And you can see that, for instance, for the states left to the crossing, they are very similar to each other in the sense that their components, electron and hole, are shifted. And so if you identify these states as a pair, in a sense, they behave similarly to how the Majorana mode behaves. In the sense that the electron and hole components of the pair as a whole have the same absolute value. The same goes for the right side of the crossing, where there's also a sign shift, but the absolute value of the components is the same if you look at the pair of states as a whole. The last model that we have checked is the 2D Chen insulator, and we have put it in junction with a normal metal. The Chen insulator is described by the block Hamiltonian that I put here on the slide, where sigma is sigmas are the Pauli spin matrices, and they indicate a pseudo spin degree of freedom, where here we interpret it as S&P orbital degree of freedom for the electrons in the system. This model has no intrinsic symmetry, and the edge state that appears depends on the boundary conditions that we impose upon the system. In our case, we are going to use periodic boundary conditions along the x direction and open boundary conditions along y. And the edge state is going to have a symmetry that is according to the x direction, meaning basically that it is going to be an eigenstate of sigma x. In other words, being an eigenstate of sigma x means that the S and P components of the edge state are going to be the same. And this is the parameter that we are going to use to see if the fine-tuned state is distinguishable or not from the topological edge state. So we have attached to this Chen insulator two different models for a normal metal. One, which we are going to call sigma zero normal metal, where the hoppings between S and S sites and P are identical. And another, which we're going to call sigma Z normal metal, where the hoppings between S and P are opposite. So as I mentioned, open boundary conditions are going to be taken along Y. So the block Hamiltonian that I've shown in the last slide was partially inverse Fourier transformed before we done our calculations. So in the following, I'm going to show the results where we set Kx equals 0 and varied the chemical potential of the normal metal and investigated whether or not the fine-tuned states were distinguishable from the true topological edge states, which have, as I mentioned, the same S and P components. So first, for the sigma zero normal metal, here I put already the topologically non-trivial and trivial cases. For the topologically non-trivial case, you see that the state that crosses zero energy, which is marked by a black dot here, has the same S and P components, meaning that it cannot be distinguished from the topological edge state. On the other hand, for the topologically trivial phase of this model, when we tune the energy levels of the normal metal to zero energy, one of the components is zero. So if we have a probe that can distinguish between S and P components of the wave functions, we can distinguish between this and the topological edge state. And finally, for the sigma z normal metal, we have done the same, except that in the topologically non-trivial phase, we cannot fine-tune the energy levels of the normal metal to cross zero energy. So what I show here in the left is just the true edge state. For the topologically trivial case, we have something similar to what has been observed for the Kitsayev chain, where you have a pair of states that approach zero energy. And as a pair, and as a pair, these states have components shifted, so they cannot be distinguished as a whole from the topological edge state. I'm going to briefly outline the conclusions here. So we have observed certain behaviors when we fine-tune the energy levels of a normal metal to cross zero energy. And when it happens, the states that emerge have similar characteristics in some cases to the true topological edge states. And this suggests that if one has access only to the energy and spatial profile of an eigenstate of their system, for example, when you use a spatial probe such as an STM, one must be careful to identify the edge state, because we have demonstrated the appearance of these fine-tuned states which mimic characteristics from the true edge states. Thank you for watching this video. Please subscribe.